I just want to make a little bit sense about the expansion of the small set that has many edges going outside. I'm not going really to prove it, but just to say what's the worst case. So when you have the set A of nodes in the Boolean hypercube, let's say that you have some size of this set A, and you want to put them in a way that has as less edges going outside that you can. So the best that you can do is to put it in a Hamming ball that has as many as A points inside. So how does the Hamming ball looks like? Let's say that it's around 0. It has radius d. It actually contains all the subsets and subsets times d. So now how many edges going outside from this ball? So every point that has Hamming rate less than the ones in it, all of its neighbors will be inside the ball. So the only ones that contribute to the edges going outside are those that are actually in the boundary of the nodes. So those of size d. So you have n choose d of those, and each one contribute n minus d edges going outside. Now, if A is of the size of the ball, and the size of the ball is approximately to the d, which is A. D is contributes. So now, actually, A and the boundary of A is approximately the same. N over A, which is exactly the density of A. Like this n just give us a normalization of the size of A. Okay, so if you believe that this is the best thing that you can do, then you get the lower bound of how many edges going outside. This is for the previous hour. I want to say something else about the previous hour, which is the Friedgut-Hunter theorem, but I guess that I will say it at some point in between the other things. So let's start here. Okay, sorry, if you remember, yes, you remember, it was not too long. we consider the Fourier characters for a Boolean function as a distribution, the set of probabilities, and we want to talk about sparse functions and concentration, and we'll see why it's important. Let's define what is a Fourier sparse function. So we say that a function, a Boolean function, is sparse. Actually, it might be also functions to the R. If the Fourier distribution is supported on a small set of characters, it's actually, if we use the notation of Hamed, then it's actually saying that the spectrum of F is bounded. Can support the same, all the characters that are not zero. We say that the function is concentrated if it is close to Fourier sparse. So here, tell me if it's true to say that just we add epsilon here. Yeah, okay. So we want, no, I'm not sure it's okay, never mind. So we want to say that the function is it's concentrated. We just say it's concentrated if it's close to Fourier sparse in L2 norm. So we talked about L2 norm, right? So why we are interested in sparse functions and concentrated functions and all of this. So one thing that we know to do with sparse functions is to learn them. We know to do it for long. Mishilevitz and Mansour, Goldwach, Levin, they show how to learn a sparse and concentrate function. And quite recently, I'm not sure what year it was. I don't know why I didn't write it here. We know also how to learn agnostically concentrate functions. So this is important. No, we just need this password to be in the bootcamp.
If you want to know more about learning, you can ask Rocco. Is there another Kalai? Like, it's not again, but other Kalai.
Oh, it's A. Okay, so one notion of concentration of distributions is Shannon entropy. So what is the Shannon entropy? I will have a definition soon, and you can think, if you're not familiar with this, you can think about it as a log of the size of the support. So just put it here. If someone doesn't feel comfortable with the Shannon entropy, then entropy roughly log formal definition is, so usually we don't write it with expectation. Maybe it was because I didn't have enough space in this slide. So the Shannon entropy, any distribution, and specifically the distribution, the Fourier distribution, is a summation over all the probabilities. Like the probability log 1 over 50. And if we know that the Shannon entropy is small, then we very easily can say that it's also concentrated. Just use a very simple Markov inequality to show that the large ones in order to be very small there, it's become with very small probability. So we have actually the probability to be small. This is exactly the L2 norm difference. So we can just remove all the small ones. Now we have that most of the rate is concentrated on just exponentially in the entropy many characters. So again, what does it mean? That if the function has lower Shannon entropy, then we can learn it. Does the opposite is true? If we have a concentrated function, we know that we have only few large Fourier coefficients. Does it mean that Shannon entropy is small? So the answer is no. It might be that we have a very small weight that spread on too many characters. So if we prove something about entropy, it will imply concentration, but not the opposite. But there is another notion of entropy. There is a mean entropy, which is, let us define it. Yeah. Mean entropy is exactly what you should think it is. Instead of taking the summation or the expectation, just the minimum over 1 over. And it's also useful to think about it like log of 1 over the maximal rate of the maximal Fourier coefficient. So even though concentration doesn't show as low Shannon entropy, it implies low mean entropy. Because if we have a small set of characters that are heavy, then at least one of them is heavy. Here's the definition of the mean entropy here. We're saying that at least one of them is heavy. It means exactly that the minimum log is small. So there is a famous conjecture in the field of analysis of Boolean functions that called the Fourier entropy influence conjecture. It's called by Friedgut and Calais, Bill Calais. Years ago, not too many, but many. Let's say that there exists for every, let's keep there exists. For every function, Boolean function, we want to bound the Shannon entropy by the total influence. So the meaning of it is that if the total influence is small, then we want to say that the function is concentrated. Yuval should be interested in this. So if it's concentrated, then we have learning, we have sharp threshold phenomena, and maybe later. Okay. We didn't success to prove it many years. Then Ryan and Donald and actually others came up with some relaxation and said, okay, if we don't know to bound the entropy, maybe we do know to bound the mean entropy, which is always smaller than the entropy. So this is another version of the Fourier entropy, and here's why about the Fourier entropy. So if this is true, we'll have also agnostically learning for DNF. And this actually non-trivial results for small influences that for influence that are not very small, but of order of log n. what we will see today is a slightly weaker version of this. We will get to it. Because it's important to know what we know. So we know the Fourier entropy influence conjecture for some specific classes. So I'll not elaborate what the classes are, but someone know them, then it's good to know that we know the FEI for them. So we have symmetric functions, read once formulas, linear threshold functions. The other, I'm not sure it's are interesting now. Now there is something interesting that I want to show. So the Fourier mean entropy influence, or everywhere that we know that the Fourier entropy works, then also the Fourier mean entropy, because it's weaker. We have other classes, and in general, we know that the mean entropy is at most the influence squared. So let's see where we know this from. So I want to show you the Fried-Guthrunter theorem, which is very important basic theorem. The Fried-Guthrunter theorem is kind of a generalization of the KKL. Right here, again, the KKL. We have a Boolean function, balanced, meaning that the expectation of f is 0. In KKL, there exists some I that the influence I of f is so what KKL showed is that there exists some variable, at least one variable that has large influence. What Friedgut said, he said all the, let's take all the influence, the variables that has large influence. And if we look at a function that depends only on them, it will be close to the original function. There exists G, function G, junta. So junta meaning that it depends only on variables. Set J. For J, which is not too large. Not too large is exponentially the total influence. So that F and G are close in L2 norm. Something about the proof idea of this. The statement is clear. we define J, the set of the variables that will be in the junta. It does that the influence is large. Constant. Then we can take just the characters, the part of F, the characters of F that contained in J, and show that the entire weight on characters that are not contained in J is at most epsilon. So we can just remove them. When we just remove them, we might end up with a function which is not necessarily Boolean, but this is easy to fix. So I'm not going into this now. So the big difference between the KKL and Friedwood is that the KKL say at least one variable, and Friedwood say, let's take the variable that promised by KKL, let's take another one promised by KKL, and all of them, and this is enough for us. So you can say that, you can see that we have at most two exponentially many in the influence variables that has a large influence. So now how can we see the mean entropy from here? There is another thing that I need for this.
Yes, question?
Yeah. You mentioned it's easy to fix the function when you remove a certain number of Fourier coefficients. It's easy to fix it and make it Boolean.
Yeah.
How do you do this?
You can just take the sign.
Oh, sure.
So not you just should pay attention that it not always works, because you need this these things to preserve what you want from the function, the properties. So here it just depends on few variables. If you take the sign, it still depends on the same amount of variables. But if you want to preserve the degree, for example, it might be not true. Okay, so the total influence. We say this is the expected degree. Take as from the Fourier distribution. So now I want to claim that every F is close to low degree function. Degree of the total influence over epsilon. Symbolization, we need this. Actually, it's proof in order to show that we get from Friedwood the mean entropy. If we just take the tail of F and remove it, we get a low degree function. Let's show that this function is closed. G epsilon F minus G L2 norm. There's a distance between them. I take the Fourier coefficients. So it's all the large Fourier coefficients. weight on large foreign coefficients, which is exactly the probability of the character S to be larger than the total influence over epsilon. Distribution of F. The total influence is exactly the expectation of S. We use Markov to say this is at most epsilon. So now, let us prove that the entropy is at most influence square. So from the proof of Friedgut, we know that the summation over all characters that are in J is at least 1 minus epsilon. And if we remove from here the characters that are larger than the total influence over epsilon, then we only lost another epsilon here. And how many characters we have here? We need to choose subsets of J of size at most total influence, and all of them are at most J. So this is at most number of characters such that S in J is at most influence F epsilon. This is at most J to the influence over epsilon, which is at most 2 to influence square. So now we have that many characters that altogether has all the weight. So at least one of them have 2 to minus the influence square weight, which is exactly the mean entropy bounded by the influence square. Okay, questions? We want to know better than that, but at least that this is, I guess, quite easy. You want me to repeat what?
Division of the third set.
The set S here. So I take all the S's that contained in J, the function, with small size, at most the influence over epsilon. So I know that all of them has at least 1 minus epsilon, and this I lose only another epsilon of the weight. And then I know that I have, this is exactly the characters that I have here. So I have almost all the weight there.
Is it a 1 over epsilon or 1 over epsilon squared in the exponent for the final time?
Sure, maybe square. Oh, yeah. It's not. Okay, so the best thing that we know today, and that the mean entropy is not only bounded by the influence square, but it's in. We want influence, but we know to bound it by influence log influence. We know also about the Shannon. Yes. Some corollaries of this. Okay, why do we care about lower degree functions? And it's very useful to say that the function is close to, if it has small total influence and close to lower degree, because we have the hypercontractivity, which is very useful improving things in Boolean functions. So what it said that for every function which exactly the exact degree is at most d, meaning that it has no weight above the degree d, the LP norm of 4, the L4 norm, is at most some constant depends on d. The L2 norm, so I'm not sure if you haven't defined the norms, but let me define it again, or in the first line. So the norm of a function, the expectation over the inputs. And I'm not going to say anything about this. I'm just going to use it as it is, and hopefully you will have more sense about it till the end of this week, maybe tomorrow morning. Okay, but let us remember it. So in order that f norm is at most 3 to the d, L2 norm is the height and this is true for every function to the r, okay? It's not only for Boolean functions, but actually for -1, 1 functions, I think it doesn't give us anything. Maybe for 0, 1. Okay, so how should we bound the entropy? So the main goal now is to bound the entropy of the Fourier distribution. And all the proof is going to use correlation between functions. We'll do it slowly, and let's see. I hope that we can prove the KKL and Friedwood at least. This is a general correlation bound. So we have the first function f is Boolean. The second function going to r, but we know about it that it's bounded degree. And we have some promise about the influences of f. We know that all the influences are small. And then what we want to prove is that the correlation between f and g, which we guess is defined at some point. Between f and g is just the expectation over all the values fx. And similarly to the Perceval, this is Plancherel or something like this, we can just take all the Fourier coefficients. You want to elaborate this step, or it's okay? Okay. I'm not going to do it. And the coarse influence between f and g is just something. Let's. I think that we can do without thinking about it too much. Okay, let's prove this. It's going to be one line using the hyperconductivity. It might not make any sense, but just use some tools. So if we think about the functions, the f and g, the correlation as the summation of the characters. We can see that every character we might allow ourselves to count characters more than one time if we assume that all the signs are the same, so all of them are positive. So now we can just say this is at most if we take the derivatives. So the derivatives, just reminds, is just all the characters that contains I for every I. Okay, so now the only thing that we change from here to here is to count every character as many times as its size. So it only can be large. And for such correlations, we can use Hölder's inequality. So we take very specific numbers for Hölder and bound the correlation with the fourth, third norm, and fourth norm. So why we choose these numbers? So we have the hypercontractivity that works for every function, not only Booleans. Therefore, we want the fourth norm because we know to bound it. We put the fourth norm on the G, which is general, and then we get the fourth, third norm on the derivative of f. So now using the hypercontractivity, we get here a factor of exponentially in D. But we know that D is a degree that G is bounded of this degree. And for the other one, this is very useful to know that this is a derivative. So we say that it takes values -1, 0, and 1. And when we take norms, the -1, 1 actually goes together. They have the same value, the same contribution. And all the norms actually equal up to some. Like it's really easy to go from one norm to another norm. I'll just apply this. Okay, so this was a short proof, maybe not very interesting for now, but let's see that this correlation actually implies the KKL. So if we take, let's assume that F is balanced, and we choose D to be twice the total inference, or we think about epsilon half. And then take G to be the lower degree part of F, all the characters that are at most D. Let delta to be the maximal inference. So now just apply this correlation on F and its lower degree part. We get that this is at most the maximal influence exponentially in D, which is the inference, the total inference now, and another inference, which is not a lot when we have exponentially in the inference. And another thing that we have to note here, once we took D to be twice the total inference, we lost only at most half of the weight, exactly the same as we did before. So we know that the correlation between F and its lower degree part, which is exactly the weight of the Fourier coefficient up to the twice the inference, is at least half, at least constant. So from here we can derive that the maximal inference delta is at least exponentially in the total inference. I guess this was shorter than what we had in the previous hour. And hopefully tomorrow you will have more sense about it. So now the question is, can we do better correlations? And this needs a bit work to make it better. So if you're not here, we just assume that all the influences are small. So now we can think about that we have some small influences, some larger influences, but as we showed in the proof of the Friedgut theorem, we can't have too many large influences. So we can just take them separately. So you can see now that we have another correlation inequality between, again, a Boolean function and the lower degree function, where now delta is for every delta. We just have two parts of the bound. One of them will be similar to what we had previously with all the influences that are at most delta. And the other one just said, okay, we don't have too many that has more than delta. And they contribute at most something trivial. This is actually the proof. Let's skip it. And see what we can imply from this. So if again we take D to be twice the total inference and delta, which is to be exponentially small in the inference, and again G to be the lower degree part, then putting all of this here in the correlation bound, we get that we have at least one Fourier coefficient, which is large, larger than exponentially in the total inference square, which gives us exactly what we know from Friedgut theorem, that the mean entropy is at most the total inference square. Any questions about it? Anything that you wanted to elaborate more? So now the question is, can we do better? We want to get to the inference times log the inference. And if you see, what we do is to apply the hyperconductivity, which we need lower degree. So maybe we can reduce the degree before we apply the hyperconductivity. And that we already know to do. We just do random restrictions, right? So we already know to do random restrictions. Yes. Let's see what we have here at the end. So if we start with some D, with degree D, and we take do random restrictions with V over D for some V, which is much smaller. So we want to reduce the degree D to degree V. So we take the random restriction to be V over D. We expect the characters to the Fourier weight from the degree D now to go to the degree most V. What we can get. Now, if we do the restriction for both F and G, this is actually the restriction. J is implicit here. It'll be hard to do it without elaborating more. Okay, so the idea is that once we do the restriction, we have lower degree, can now apply the hypercontractivity with the lower degree. We get now exponentially in V here. And we always have the other part. So we can repeatedly do this process again and again. We take how many large parts we have, we apply the hypercontractivity, apply random restriction. And if we do it enough times, we finally get to the log. Somehow we can't do better than that. So this is actually, we applied the previous inequality.
Oh, no, I mean the first equality.
Oh, the first equality? Okay, yeah. So actually, this is interesting. So you can think about it that you take, actually, when you do random restriction, you first choose what variables are going to be alive. So here we are after this. We do only expectation over z, which is actually what part of the hypercube we choose. We can actually get a partition of the hypercube for subcubes when each z just choose a different hypercube and they have no intersection. So when you do expectation over all the function or over just the subcubes, and then expectedly over all of them, just linearity of expectation, you get the same. Yeah, this is nice observation from here. Maybe the most useful one.
Sorry, if you just want to improve that power 2 to say 2 minus epsilon, is it enough to do one round of this instead of recursively?
If I
So what you get from Friedgut is you get this mean entropy is at most c times I squared, right?
Yeah.
If you just want to improve that 2 to say 2 minus epsilon, do you have to do this recursion, like repeatedly do?
I'm not sure that I understand where do you refer exactly. Let's take it offline. I guess that we skip this. Yeah, it's in purpose. Okay, so here the main thing that I want to say about all of this is that that we can do such correlations, very general bounds on correlations that we think about. Just one function is bounded degree and the other function is Boolean. And the idea of once we have this bounded degree, we do random restrictions, we lower the degree, we can do it again and again until we have the result that we want. Another thing that I want to show, and I hope that I can show, is about concentration. Understand this. So actually, the idea about the concentration is to show that we have most of the weight on very few number of Fourier coefficients. And another notion of this is the L1 norm of the Fourier coefficients. So let's say that we have summation of the Fourier coefficients. Let's say that we know how to bound the summation of the Fourier coefficients, the L1 norm, with some L. Maybe I can give an example. Yeah.
Where are we trying to put that?
So we just moved to something else, another notion of concentration.
Okay.
Okay. Of Fourier coefficient. Yeah, okay. I just wonder whether we can do about decision trees. Of for example. So, okay, what is a decision tree? We have a tree that we can query one variable, which is, let's say, some xi. And if it is 0, we go here. If it's 1, we go here. And then we can query another variables. Go there. And on the end, on the leaves, we have values. Let's say each leaf is either 0 or 1. So this is a way to compute a function. If a function is computable by a small decision tree, then we can know some things about this function. For example, we can bound the L1 norm of the Fourier coefficients. So if we have in the decision tree at most L nodes, we can show that the L1 is at most L. The way to do it is quite easy. We do it inductively. So every leaf can contribute at most 1, because this is only one, this is constant function, or you can go above, this is just a dictatorship. And when we combine two functions, we can see that it can combine at most the amount of both the parts. So for example, this is going to be interesting for decision trees. Plane. Bounded. Concentrated. How can we see it? So let's see how many Fourier coefficients larger than mu we can have. So let S be such that Fs is at least mu or some mu. So how many of these we can have? So here it's useful to look at the Fourier coefficient squared. This equals 1. This is at most the number of this that we have here times mu square. And this is at most 1 over mu square. So whenever we want just to say that we have at most mu, at most coefficients that are larger than mu, we have at most 1 over mu square. But what is the reasonable mu to take here? So we need to show that all the others that are outside mu contribute not too much. If we take the summation over all S such that the Fourier coefficient is at most mu square. Now we can take we know something about the L1. So let's take the maximal outside times the L1. So the maximal we know is at most mu, and the L1 is L. So we have at most M over L. If we want this to be at most epsilon, we just choose mu be epsilon over L. And then we get here L over epsilon. So this is another way to show concentration. I'm not sure.
Goal. Yes, I commented on this, right? I'm trying to ask it again.
Oh, I mean, it's just pretty technical. I was just wondering, yeah, I think it's here. I guess you have to look at the proof here.
Okay, sorry, thank you.
Reception, and tomorrow we'll meet. So food will be served at 9 a.m. if you make it that early here, like I probably won't. And the talks will start at 9:30. So tomorrow we have in the morning Elie Dinou. She's going to introduce high-dimensional standards and so we're going to learn some, but it's cumulative algebra. It's all going to be linear algebra, but very strange. And then in the afternoon, Noah will talk about heavy conductivity and also applications in extreme combinatorics.